When engineers design something, we try to balance cost and performance. For performance, we often try comparing against a best-case scenario. You do the same thing when you're shopping. If you're buying a computer graphics card and watching reviews, then you'll see that cards are tested in benchmarks against the best hardware that's available. If you're a savvy shopper seeking great value, then you want to find a product with performance that might not be quite the best, but hopefully is a lot cheaper than the flagship option. We wanted to be savvy when designing receivers for diffusion-based molecular communication. In molecular communication, a transmitter releases molecules encoded in a molecular signal, the molecules travel through the environment, and a receiver watches the molecules to recover the messages. This approach is used by cells to share information, and we wanted to know what were the physical limits. We wanted to figure out the best possible receiver, then see if we could get close to optimal performance with simpler designs that could be easier for engineers to build or for living cells to have evolved. Our challenge is that diffusion is very noisy. The signal will go up and down as molecules enter and exit the view of the receiver. If we only take one measurement, it could be weak, it could be strong. So how can we deal with unreliable measurements? Well, we can take multiple measurements. If we sample the signal more often, then we take in more information, and that reduces the effect of the diffusion noise. There are practical limits to this, though. We can't improve performance if we measure faster than how long it takes for molecules to enter and leave. We were studying a communication system where the transmitter sends a sequence of bits, ones and zeros, and does this one at a time by releasing or not releasing molecules. This is called on-off keying. Diffusion adds noise and it adds delay. So molecules that were intended to communicate one bit might not arrive until you're expecting molecules for a later bit. While a simple receiver benefits from having a mechanism to break down the signal, the best approach is to just keep taking samples and not make a decision about any bits until the whole message is transmitted. Then, if you know the statistics of the channel, then you can reconstruct the most likely sequence of bits. However, this optimal approach is extremely expensive. A sequence of 30 bits would require comparing 2 to the 30 different possibilities, or just over 1 billion options. We can make some assumptions to substantially reduce the number of possibilities, but this approach is still impractical for devices with very limited computational power. We published a paper in 2014 that described this best approach and how frequently a receiver can take samples. We compared this optimal receiver with simpler designs that still use multiple samples but decide each bit shortly after transmission. While there are cases where the optimal receiver is way better, there are also cases where simpler designs can get very close to optimal performance. This happens when there is something in the environment to help break down the signal, like enzymes or fluid flow. We can actually get great bang for our buck without paying the full price of large memory or computational resources. This makes us great savvy shoppers in the world of molecular communication. Thanks for watching this micro abstract. This series summarizes our research publications. If you liked it, let me know. If you really liked it and you want to see more research highlights and tutorials on biophysical communication engineering, then you can subscribe and check out the other videos on the channel. See you next time.